Welcome to the online course on pericyclic reactions and organic photochemistry. We are in module number 21. We continue with pericyclic reactions in sigmatropic rearrangement. There is a small portion under Wittig rearrangement and higher order sigmatropic shifts will be considered in this particular module. Now let us first consider what is Wittig rearrangement. This should not be confused with Wittig reaction, which involves phosphorus elite for the synthesis of olefins. Wittig reagent is a 2,3 sigmatropic rearrangement of an alpha allyl oxycarbanion. If you consider this benzyl allyl ether, when you treat it with butyl lithium for example, it undergoes rearrangement to give 2,3 rearrangement as well as 1,2 rearrangement. We will look into the mechanism of these two rearrangement processes as follows. If butyl lithium is treated with this particular benzyl allyl ether, the most acidic hydrogens are mentioned as the benzylic hydrogen. So the deprotonation of the acidic hydrogen in the benzylic position leads to the benzyl anion. That benzyl anion is capable of undergoing a 2,3 sigmatropic rearrangement, which is represented by the cyclic arrows that are shown here. Now this is a 6-electron 5-membered ring transition state type of rearrangement where the carbanion that is generated reacts to the terminal position of the allyl group followed by rearrangement with the breaking of the carbon-oxygen bond of the ether in this particular instance. That corresponds to the 2,3 sigmatropic rearrangement corresponding to this particular product formed upon workup by treatment of this anion, alkoxy anion with an acid. Now how is this 1,2 Wittig product formed? 1,2 Wittig product is formed by the same carbanion reacting not in the allylic terminal position but in the allylic position, in this position here, in this carbon here, thereby undergoing a 1,2 shift kind of a rearrangement resulting in the formation of a 1,2 Wittig product. Oftentimes a mixture of 2,3 Wittig product as well as 1,2 Wittig products are formed. There is some control over the 1,2 versus the 2,3 using the polarity of the solvent. Normally the charge polarization or the charge delocalization is much higher in the 2,3 sigmatropic rearrangement compared to a 1,3, 1,2 sigmatropic rearrangement of this type. Therefore, polar solvent should favor the formation of the less delocalized structure of this kind, which will result in the higher amount of formation of the 1,2 Wittig reaction. Non-polar solvents would generally favor the 2,3 Wittig reaction in general. Now, the Wittig rearrangements are highly diastereoselective in nature. You can see here by taking the E olefin in this particular instance, and Z E olefin mixture to the extent of 83:17 is formed for the allyl alcohol that is formed, homoallyl alcohol that is formed in this rearrangement. Here again the benzylic anion is generated that undergoes the rearrangement, 2,3 rearrangement with the breaking of the carbon-oxygen bond resulting in the formation of this homoallyl alcohol. Suppose if you take two diastereoisomeric system with a propargyl ether, in other words this is an allyl propargyl ether kind of a system is what is represented in these structures. This is the E isomer of the propargyl allyl ether and this is a Z isomer of the propargyl allyl ether. Upon treatment with butyl lithium, the carbanion that is generated in the propargylic position, which is the most acidic hydrogen in this particular case, undergoes 2,3 sigmatropic rearrangement even at minus 85 degrees quite rapidly to give to an extent of 99% of the diastereoisomer, which is the anti-diastereoisomer as indicated by the stereochemistry of the methyl and hydroxy being anti with respect to each other. On the other hand, when the Z isomer is treated with butyl lithium, again the propargyl anion is generated which undergoes the 2,3 sigmatropic rearrangement at a very low temperature. You get exclusively only the syn diastereoisomer to an extent of about 100% diastereoselectivity. So these two examples clearly illustrate two things. One is that the 2,3 sigmatropic rearrangement is the predominant process in these cases, and the rearrangement is highly stereospecific in nature in the sense that the starting material double bond stereochemistry really matters in terms of the stereochemistry of the product, homoallyl alcohol product that is being formed in this particular system. And this involves essentially a tight 5-membered 6-electron transition state which leads to the high diastereoselectivity in this kind of reactions. Now the Wittig rearrangement, 2,3 Wittig rearrangement has been put to use in the synthesis of an insect pheromone. Insect pheromones are chemical substances that are secreted by insects for communication purposes among the same species. For example, it could be attracting a male, the female may be excreting the pheromone, which is this particular pheromone, and so on. So these are essentially signaling chemicals which are secreted by insects. In this particular instance, this optically pure isomer of this particular propargyl allyl ether is treated with butyl lithium. Again, a propargyl anion is alkoxy anion is generated here, which undergoes the 2,3 sigma tropic rearrangement. In doing so, there is a chiral induction that takes place because this is a first order asymmetric transformation. Your starting material is optically pure with this particular configuration. Upon rearrangement, it undergoes highly diastereoselective syn type of a product is what is obtained through a 5-membered cyclic transition state involving 6 electrons in this species. The chemical yield is 98%. The diastereoselectivity is 98% of this particular diastereoisomer. If you call this as a syn isomer, the anti-isomer is not formed more than 2% extent in this particular instance. And the major diastereoisomer, which is a syn isomer, is formed in 98% of enantiomeric excess. In other words, this particular configuration of the molecule is obtained in about 98%. The other configuration molecule where you have these two chiral centers in a different configuration, for example with thick lines representation, that would correspond to about 2% of the material that is formed in this case. This material is a starting material for the elm bark beetle pheromones minus isomer, which is this particular structure here. So this is an instance of the 2,3 Wittig rearrangement being put to use for the synthesis of an insect pheromone, which is useful, for example, in naturally eliminating the insects, a natural way of eliminating the insect, for example. As a natural insecticide, it can be used. Dipropargyl ethers also undergo Wittig rearrangement. Here is an example of a dipropargyl ether treated with N-butyl lithium and tetramethylethylene diamine. Now, N-butyl lithium tetramethylethylene diamine is a powerful combination in terms of making the butyl lithium even a stronger base than it is. The tetramethylethylene diamine is essentially complex to the lithium. As a result of this, free butyl anion is generated under this condition. In other words, the lithium is chelated by the tetramethylethylene diamine, resulting in the formation of a highly ionized form of the N-butyl lithium, which is a stronger base than butyl lithium itself. That results in the generation by deprotonation of the hydrogen from this position, generation of this propargylic alkoxy propargylic anion, which undergoes the 2,3 sigma tropic rearrangement as shown by this arrow, involving a 6 electron 5-membered ring cyclic transition state, resulting in the formation of this allene derivative, which is the final product of this particular reaction. Now, the alkoxy anion that is generated in the previous example, propargylic and allylic oxy anion, they undergo the Wittig rearrangement. One can also generate in situ a oxygen based ylide that will undergo the 2,3 sigma tropic rearrangement. Here is an example of an alpha diazo ester being decomposed in the presence of rhodium to generate the carbene. That carbene reacts with the oxygen lone pair to give the corresponding oxygen ylide. That the oxygen ylide undergoes the 2,3 sigma tropic rearrangement to produce these products that are formed during the course of this. So this ester fragment essentially comes from the alpha diazo ester by the decomposition. The mechanism is shown here. The alpha diazo ester transfers the carbene onto the oxygen, resulting in the formation of this particular oxygen based ylide. The oxygen based ylide undergoes the 2,3 sigma tropic rearrangement to produce this product. And you can see also here the diastereoselectivity is extremely high for this rearrangement because of the well-defined stereochemistry, which is the trans stereochemistry of the double bond, and the well-defined 5-membered cyclic transition state, which results in the high diastereoselective formation of only one isomer in this particular instance. The diastereoselectivity is also high when the rhodium is complex to this particular chiral ligand. The chiral ligand induces the chirality of the chiral induction of the product that are being formed. The high enantiomeric excess that is obtained for these two products and the high diastereoselectivity obtained for these two products are synthetically very useful transformation in terms of making such molecules using a 2,3 Wittig rearrangement reaction. Here is an example of an intramolecular transfer of a carbene from the alpha diazo ester. This is the alpha diazo ester with the oxygen, which is this particular oxygen lone pair is capable of trapping the carbene that is generated by the decomposition of the alpha diazo ester in the presence of copper tetrafluorophosphate, for example. Now the ligand that is used is a chiral ligand. So asymmetric induction, again it is a chiral Lewis acid catalyzed asymmetric induction is what is taking place in this particular instance. This is a proposed intermediate, which is the oxygen based yelid intermediate, which undergoes 2,3 sigmatropic rearrangement. So you can see here this is the allylic ether part of it, and this is the yelid part of it. So if you take the carbanion and react it in this position, and concomitant rearrangement of the pi bond with the breaking of the carbon oxygen bond will result in the formation of this ring contracted product, which is a 10-membered lactone using the 2,3 sigmatropic rearrangement or the Wittig rearrangement in this particular instance. Here is an example of an aza 2,3 Wittig rearrangement. Instead of an oxygen, if you have a nitrogen that is present in the allyl benzyl amine kind of a system, instead of allyl benzyl ether kind of a system, then it is called the aza 2,3 Wittig rearrangement. The aza 2,3 Wittig rearrangement is also triggered by the generation of the alpha anion of the amine by treatment of the amine with N-butyl lithium in HMPA as a solvent. Hexamethyl phosphoric triamide is the solvent here at minus 78 degrees centigrade. The rearrangement is essentially occurring from the carbanion that generated in the benzylic position, which attacks the allylic terminal position with a concomitant rearrangement followed by the carbon-nitrogen bond cleavage, resulting in the formation of this Bach protected secondary amine in this particular case. And once again, the diastereoselectivity is very high because of the well-defined stereochemistry, which is the trans stereochemistry in this particular. The cyclic transition state structures are indicated here. There are two possible conformers which can exist in a cyclic transition state. In this conformer, the X group and the phenyl group are sterically interacting with each other in a hindered fashion, which is absent in the case of this particular transition state, resulting in the formation of the anti-isomer of the product that is formed using the aza-Wittig reaction in the aza-Wittig rearrangement in this particular instance. Now let us move on to higher order sigmatropic rearrangement. These are rearrangements which involve 6 electron or more. So far we have looked at 4 electron and 6 electron involvement of the sigmatropic rearrangement. In this particular section, we will look at the higher order sigmatropic rearrangement that involve more than 6 electron. The very typical example of a 10 electron system involving a 5,5 sigmatropic rearrangement is the pentadienyl phenyl ether. If you look at this molecule here, this is a phenyl ether and a pentadienyl ether. So it is a pentadienyl phenyl ether is what we are referring to. When this is refluxed in diethyl aniline, which is a high boiling solvent at 185 degrees Celsius, there are two products that are formed. The first product is resulting from a 3,3 sigmatropic rearrangement. You can see here this can undergo a this is something like allyl vinyl ether, so it can undergo a 3,3 sigmatropic rearrangement resulting in the formation of this product. It can also react in the para position, which would be a 5,5 sigmatropic shift. These two mechanisms are depicted in this particular in this slide here. The black arrows essentially indicate the 3,3 sigmatropic process. So if we just follow the black arrows that is shown in this particular structure, that will lead to this particular product. This particular product can further undergo a 3,3 sigmatropic rearrangement to give this product, or it can undergo simply a keto-enol tautomerism to the observed product, which is the 3,3 product. This particular product is what is obtained here, and that is the same product that is mentioned here, arising out of a 3,3 sigmatropic rearrangement. Now if you consider the red arrows, which involves 10 electron system, this is a pentadienyl phenyl ether kind of a system that will essentially rearrange the pentadienyl group to the para position by reacting the terminal carbon of the pentadienyl system with the para position of the aromatic system. The chain is long enough to reach the para position. That is why such a reaction is a facile reaction. So under this condition, if you count the number of atoms involved, this is the carbon oxygen bond that is going to break. So if you start counting from there, this is 1 and 1, oxygen is 1 and this carbon is 1. Then 2, 3, 4, 5. So this is 1, 2, 3, 4, 5 on the pentadienyl system. and 1, 2, 3, 5 up to the para position of the phenyl ring from the oxygen. So the carbon-oxygen bond is what is breaking in this particular system. So the nomenclature wise, this would correspond to a 5,5 sigmatropic rearrangement. After the 5,5 sigmatropic rearrangement, the ketoenol tautomerism will essentially produce this particular phenol. You can see here the terminal R group is now attached directly to the benzene ring. That carbon is directly attached to the benzene ring. Detailed mechanistic studies have indicated that this particular product is obtained only from a 5,5 sigmatropic rearrangement, ruling out the possibility of sequential 3,3 followed by a 3,3 sigmatropic rearrangement. If you look at this particular product, this would rather undergo a ketoenol tautomerism to give this particular product than to undergo further the 3,3 sigmatropic rearrangement under the reaction condition. So deuterium substitution labeling as well as the kinetic measurements very clearly tell that this is a product arising out of a 3,3 sigmatropic rearrangement, and this is a product that is arising out of a 5,5 sigmatropic rearrangement involving 10 electrons during the course of the rearrangement. The sequential 3,3 sigmatropic rearrangement, although it can also in principle yield this product, that has been ruled out based on mechanistic study. So this particular process that is shown by this arrow here, it is a ruled out process based on the mechanistic study by the scientists. Now the most famous 5,5 sigmatropic rearrangement in aromatic chemistry is the rearrangement of hydrozobenzene under acidic condition to benzidine. This is the rearrangement where the hydrozobenzene is under hydrochloric acid conditions, concentrated hydrochloric acid condition. When it is heated, it undergoes a 5,5 sigmatropic rearrangement to give the parabenzidine as the product. The suggested mechanism is that the protonated hydrozobenzene, essentially the two benzene rings lie parallel to each other, bringing the para positions in close proximity together. It's as if their pi-pi interaction is there between the two aromatic ring, resulting in the interaction between the para positions and formation of a sigma bond here. If we consider the breaking of the nitrogen-nitrogen bond, then from this nitrogen it will be a fifth carbon, and from this nitrogen this again will be a fifth position. So overall it is a 5,5 sigmatropic rearrangement. Such a rearrangement essentially produces this molecule, which is an intermediate in this particular case. This is a 5,5 sigmatropic strip. From here, tautomerism essentially results in the formation of benzidine, which is a final product in this particular instance. Now here is an example of a pentadienyl oxypyridine N oxide as a substrate. There are two reactions that are taking place here. One is obtained, one of the product is obtained by a formal 1,4 shift of the pentadienyl group. The other product is obtained by a 5,5 shift of the pentadienyl group onto this particular position. The mechanism of these reactions are very clearly indicated here. This is by the reaction of the oxygen onto this position here with the cleavage of the carbon-oxygen bond. So if the carbon-oxygen bond is being cleaved, then it will be 1 and 1. This is 1, 2, 3, 4. Between the two oxygens there are 4 atoms, and between the C substituted with the 2 X groups here, essentially this is a 1,4 kind of a rearrangement is what is taking place. You can see here solvent has a major effect on the distribution of these two types of products. In the 1,4 rearrangement, essentially there is a delocalization of the charges. In other words, the charge is dispersed between these 5 atoms that are involved in the reaction. So the low polarity solvent essentially favors the solvent of low polarity or dielectric constant favors the 1,4 shift, whereas the 5,5 rearrangement, which is the pentadienyl rearrangement undergoing a rearrangement at this position here, resulting in the formation of this particular product, the charge dispersion is bare minimum. So polar solvents essentially favor that particular product formation under this condition. So solvent polarity plays a huge role in promoting 1,4 in the nonpolar solvents and 5,5 in the polar solvents, as CCl4 and DMF are used in this particular reaction to illustrate this particular point. Here is a very interesting photochemical 3,5 sigmatropic rearrangement. 3,5 sigmatropic rearrangement under photochemical conditions should be suprafacially favored. It is a 8 electron system essentially. 8 electron system under photochemical conditions should be suprafacial. Under thermal conditions should be anterofacial, like a 4n electron system that we normally discuss. The system that is undergoing the rearrangement is clearly, the skeleton is shown in this particular case. This is a carbon-carbon bond that is going to break. If the carbon-carbon bond is breaking here, then it will be 1, 2, 3, and this will be 1, 2, 3, 4, 5. So the terminal of this carbon and this carbon containing this fluorine are the carbons that are interacting during the course of the rearrangement. The rearranged product, which is a 3,5 rearranged product, is shown here. The rearranged product is under the photochemical conditions also undergoes a 2+2 cycloaddition reaction leading to the formation of the cyclobutane derivative, which is this particular derivative. The cyclobutane is a vinyl cyclobutane. It readily undergoes a 1,3 sigmatropic rearrangement to give this particular product. The arrows very clearly indicate the 1,3 sigmatropic rearrangement, and the other product is essentially formed by a 2+2 cycloaddition reaction, straightforward 2+2 cycloaddition reaction of the starting material. In fact, product A arises by a sequence of 3,5 sigmatropic rearrangement followed by 1,3 sigmatropic rearrangement, whereas product B arises by a 2pi cycloaddition reaction between this double bond and this double bond here, resulting in the formation of this cyclobutane by a 2+2 process. It has also been shown that the product B under the photochemical condition does not isomerize to product A, which rules out the possibility of the product B as an intermediate for the formation of product A in this particular case. Nitrogen ylids undergo a 4,5 sigmatropic rearrangement. It is involving 10 electron system, and this is an illustrated example of that particular rearrangement. The nitrogen ylid is generated by deprotonation of the quaternary ammonium salt in this particular instance, and you can see here the mechanism of this reaction essentially involves 10 electrons. If you count the number of arrows, that will be 5 arrows corresponding to 5 into 2 10 electron system. So it is a 9-membered ring transition state involving a 9-membered ring with a 4,5 sigmatropic rearrangement. Why is it 4,5? This is the carbon nitrogen bond that is undergoing the cleavage. So it will 1, 2, 3, 4, 5. This is a 5 carbon chain that is undergoing the rearrangement. From the nitrogen, it is nitrogen 1, 2, 3, 4. This is the terminal position where the carbon-carbon bond is formed. So overall it is a 4,5 sigmatropic rearrangement involving a 10 electron system as shown by the arrows in this particular case, leading to the formation of this tertiary amine, which is a allylic tertiary amine in this particular instance. Finally, we will conclude this session with an all-carbon 5,5 sigmatropic rearrangement. So far we have considered the 2,3 sigmatropic rearrangement and 5,5 sigmatropic rearrangement, and they are all not involving all carbon system. At least one heteroatom in the form of oxygen or nitrogen is involved. Here is an example of a 5,5 sigmatropic rearrangement of tetrahydroheptylene derivative. This particular derivative, this undergoes isomerization back and forth through a 5,5 sigmatropic rearrangement. The 5,5 sigmatropic rearrangement is essentially facilitated by the interaction of these two carbon, which is the carbon R substituted carbon with this R substituted carbon, resulting in the formation of a 5,5 sigmatropic rearrangement. Why is it a 5,5 sigmatropic rearrangement? If you look at this carbon-carbon bond here, this is carbon number 1, 2, 3, 4, 5. So this will be essentially the breaking of this carbon-carbon bond is what is taking place. 1, 2, 3, 4, 5. This is 1, 2, 3, 4, 5. So the resulting the carbon-carbon bond that is breaking is this particular carbon-carbon bond, resulting in the formation of this particular product. This product, as it is not stable under the reaction condition, it rapidly undergoes a 1,5 hydrogen shift. A sequence of 1,5 hydrogen shifts also take place under this condition. So this is the first example of a fully carbon substituted system that undergoes the 5,5 sigmatropic rearrangement as an illustration of this example. Now in this module, what we have seen is the specific reaction of Wittig rearrangement, which is a 2,3 sigmatropic rearrangement of some nitrogen ylids and oxygen ylids, which are also constituting a 2,3 sigmatropic rearrangement. Then we moved on to higher order sigmatropic rearrangement involving 3,5 sigmatropic rearrangement involving 8 electrons. Then we had a system of 4,5 sigmatropic rearrangement involving 10 electron, and finally an all carbon system of sigmatropic rearrangement involving 10 electron, which is a 5,5 sigmatropic rearrangement. Thank you for your kind attention.